Right, so what is expected value? So expected value is an application of probability that involves the likelihood of a gain or a loss. Right? And it is stated as a dollar amount. So it can be used a lot in business, insurance, and many situations in your daily life. So a lot of examples that that you'll see in the notes and in the practice problems are about bidding on contracts for for construction, or winning probability of winning a game that where you can win money, or winning some sort of prize where probability is involved, right? So the expected value is how much we expect to either gain or lose based on those different scenarios, right? And we use this, so it's only accurate in the long run, as with many it's a common characteristics of probability, right? Right? When we think about how do we increase our accuracy when we're doing an experiment, and we want to increase our accuracy of getting our experimental probabilities, so we actually get as close as we can to our theoretical probabilities, what we should get, right? We want to do as many trials, or survey as many people as we can, or get that sample size as high as we can without as high as we are able to. So very similar here, right? We want a large sample size for this to work. And this is the key formula here, right? So we have EV, short for expected value, equals the probability of winning a certain amount times the prize that you win minus the cost, plus the probability of winning another amount times the prize minus the cost, right? So we do that as many scenarios, different scenarios as we can to win. And then we minus the probability. So make sure, right, the last term should always be subtracting, right, that last term, which is the probability that we lose times the cost it was to play or bid on a contract, or whatever the scenario is. And the expected value can either be positive, which means that we expect to gain, right? We should play, or we should bid on the contract, or it can be negative, which we expect to have a loss. So we shouldn't, in this case, we shouldn't be playing the game, or invest, or bid on the contract. And then there is scenarios where it will be zero. It can be zero, and that just means it's fair, 50-50, right? We don't really expect to gain. We can't really tell if we're going to gain anything or lose anything. So it's kind of fair play when the expected value is zero. Right? And then we went through this example here where we put the formula, we applied that formula there. That can be a little confusing when you don't see it in action. So in this scenario, in this example here, we had a game at a summer fair, consists of drawing marbles from a bag. So we had 10 red marbles, 30 yellow marbles, and 60 white marbles. So a scenario that we're used to. But this time, there are prize amounts associated with what marble we pick out of the bag. So if we draw a red marble, we win $25. If we draw a yellow marble, we win $7. And if we draw a white marble, we win nothing. And it costs $3 to play the game. Right? So we have our formula. So we can either win, when we draw a red marble, we win $25. If we draw a yellow marble, we win $7. So there's two different ways we can win money. Right? So we have the probability that we can win $25, right? Times the $25 we win minus our cost, which is $3. And then we can also win $7. So we add times the probability that we win $7 times, right, the $7 that we win minus the cost. And then those are the only two ways that we can win money. The only other way, right, the only other marble we can draw is white marble. And that means we win nothing. So we lose, right? And that is just the probability that we lose times the cost. So in this case, in terms of calculating probability, the probability that we win $25 right, is the same as the probability that we draw a red marble, right? Because when we draw a red marble, we win $25. So it would just be 10 over 100, right? There's 10 ways, 10 different marbles that we can draw that are red, and there's 100 different marbles in the bag. And then the probability that we can win $7 was just the probability that we draw a yellow marble, right? So it's 30 over 100, and then minus the probability that we lose, which is the same as the probability of drawing a white marble. So it would be 60 over 100. So we plug that in, right? Calculate each term, and we see that we get our expected value is $1.60. So that's how much we expect to win for each game. And then, right, we ask ourselves, is it worth playing the game? Should we play the game? And since it is positive, right, we expect to win $1.60. We expect to gain money in the long run, so we should indeed play the game. Yes, and that's because it's positive, right? Expected value is positive, we should play. For the second part here, part C, we didn't quite get to yet, but it's asking if you were to play the game 125 times, how much would you expect to win / lose? Well, in this case, right, we're expected to win. So if we win, so $1.60 is the expected value that we expect to gain in one game, right? So the amount that we expect to win in 125 games would just be, right, $1.60 times the 125 times that we play, right? And if you plug that into your calculator, you should get $200. Right? So if we play 125 times, we expect to win $200. So that would be how you answer this expect to win, lose in this example here. Right, so let's do another example. This one here. So with this one, we're throwing a dice. So this is on page 71 here. Right, so we want to calculate, so we're given a 6-sided dice is rolled. If an even number is rolled, you win $3 if it's even. If an odd number is rolled, you win. If an odd number is rolled, you win $0, right? And it costs $1 each time you roll the dice. We want to calculate the expected value of each game. So we have expected value equals. So right, the probability that we win, right? So we can there's only one scenario where we win something, right? It's $3. So the probability we win $3 times the amount that we win, which is again $3, minus the cost, right? Our cost is $1. It costs $1 to roll the dice. And then that's the only term that we have to win. That's the only scenario where we win, right? The other scenarios, we roll an odd number, we win $0. So we minus the probability that we lose times the cost, which is $1. Right? So the probability that we win $3, right? Will we win $3 when we roll an even number? So it's a 6-sided die. So when we roll either a 2, a 4, or a 6. So there's 2 different cases where there's 3 different scenarios where we win $3. So it's probability of winning $3 is 3 over the total amount of ways that we can roll the die, right? Which is 6. So it's 3 over 6 times 3 minus 1, which is 2. Probability we lose, well, it's just the probability that we roll an odd number, which is 3 over 6, right? Either a 1, a 3, or a 5 times 1. Right, so what we have here is $1, minus, this is just going to convert the fraction to a decimal because we're dealing with money. And so we have our expected value that we are expected to win is 50 cents. Right? And again, should we play the game? Yes. We should. Since the expected value, right, is 0, well, it's 50 cents, which is positive. And then part C is asking the same as before, right? If you were to play the game 75 times, how much would you expect to win, lose? Well, this is the amount we expect to win in one game, right? So 50 cents. So the amount we expect to win in 75 games would be 50 cents times 75. And that gives us $37.50. So $37.50. So I want to do one more example, which is on the next page. So yeah, I'll do the example on the next page. So any questions on expected value? Okay. So for this example here, again, it's a charity holds a raffle. Each raffle ticket costs, right? So costs $5, and each raffle ticket costs $5, and a total of 2,000 tickets will be sold. Below are the prizes. So one ticket will be $2,500, 4 will be $75, and 20 will have a prize of $25. So we want to calculate the expected value of each ticket. So expected value. How many ways can we win? So the first example we did, where there was 2 ways to win. The last example we did, there was only 1 way to win, right? How many ways can we win in this example? 3. Yeah, we can, right? 1, 2, and 3. So, right, if we do the first one, the probability that we win $2,500 times 2,500 minus the cost, right, which is 5. And we're adding up all those ways we can win. So the probability that we win $75 times 75 minus 5 plus the probability that we win $25 times 25 minus 5. And those are all the ways that we can win. Right? So now we minus the probability that we lose times the cost. Again, that make sure that is a minus there. The last term should always be a negative. You're minusing. What would be the probability that we win $2,500? Sorry? Yeah, okay. Yes, that's the probability that we win $25. So I said 2,500. So be, yeah, so you're right for $25, but the probability that we win 2,500 would be the same idea. 1 over 2,000. One out of the 2,000 tickets we sell, right? So this is the total tickets we sell, and one of those tickets will be the grand prize winner. So times 2,495, right? So now it's just 4 out of those 2,000 tickets will have a prize of $75, and 20 of the 2,000 tickets we sell will have a prize of $25. So how many tickets give you nothing? Or essentially you lose money. Well, how many tickets result in a win? Yeah, so 25 win. So there's yeah, so 2,000 minus 25 all over 2,000. 1975, yeah. Right, so now if you plug this in to your calculator, you should get these numbers here. Plus 0.2 minus 4.9375. So I just rounded to 4 decimal places when calculating each term. But when I sum these up, or when I calculate this, I get negative 3.35. Yeah. This way? Oh, sorry. Right, and then so I round my final answer to 2 decimal places because we're dealing with money, right? So we always just round to just the nearest cent. So in this case, we lose, right? We get a negative number. So in this case, we're losing. We expect to lose money. So should we play it? No, right? No, we should not. Since the expected value, right, is negative $3.35 is negative. And if we were to play the game 98 times, how much would we expect to lose? Well, we expect to lose $3.35 in one game. So we times that by 98 to get the amount of money that we expect to lose in 98 games, which would be 300. It would be negative as well, right? So it would be negative $328.30. And again, just rounding to 2 decimal places because it's 30 cents, because we're dealing with money. Any questions on expected value before I let you kind of have the rest of the class? Okay. So there's no questions. You have the rest of the class